Okay, welcome to this lecture 8 and part 2 of that. In part 1 we saw how we can represent various sources involved in that is sinusoidal sources, and how those sources are represented in as a phasors. Okay, so representing sources as phasors gives us definite advantage in certain kinds of calculation as opposed to sinusoidal representations of sources. So after these sources, we'll see that how the various circuit elements, that is RLC elements, are represented in their equivalent phasor forms, you can say, or equivalent forms for steady state analysis. Okay, so first we'll take resistance, and we'll see how resistance is represented. So first we'll see how it is represented in time domain, that is if you say sinusoid, that is sine omega t, then it is time domain representation of resistance. And how it is represented, it is suppose this is the voltage source representation in time domain or sinusoidal representation, root 2v. V is the RMS here, so peak times sine omega t is a usual representation of source. And then you have a resistance over here. So if you go by relations of I, and this is I here, I and V, then you can write in instantaneous terms V is equal to R times IT, or IT is equal to V by R. Okay, and you can put V as this, and that will be the IT. So IT and VT will have same form, okay, same frequency, omega t, omega, only the difference will be in their peaks, you can say. Okay, so RMS values here will be root 2 RMS by R. That will be, so if this is your VT, then RT is also having the same frequency and same phase. Okay, so IT would be like this, and IT you can say is same root 2 V RMS, or V here we are taking for RMS, sine omega t upon R, and this was same IT is this. And that is how the R and V relationship exists in a circuit. Okay, it's quite this one, and we are talking about steady state, please remember. So in any case, R and V in resistance, I and V have an instantaneous relationship. So that is what we have here. Now let us see how we represent a phasor form. Okay, so here the same voltage is represented by phasor V. Okay, or normally we'll call it as V angle 0. Okay, so V bar is V angle 0 here according to this, because the phase is 0. And then this is resistance, and let's say this is the current flowing. Then we have this relation V is equal to IR, and if you see, this relation actually exactly fits with this. Okay, so in phasor domain, only the thing here is this is a phasor quantity, and this is also a phasor quantity, and this is a value of R. And as far as resistance is concerned, this relationship is quite similar, except for the way we write. So if this is taken as V, then I will be in phasor form will be something like this. Okay, and it is V by R. So they are in phase, both are in phase. So now let us go to other circuit elements. So other circuit element which we are going to see now is capacitor, and this is the same time representation VT, that is source, and this is the capacitor C, and we know in a capacitor the current and voltage relation is ICdV by dt. Okay, so we are always talking about steady state. Don't imagine what happens when t equal to 0. We are imagining that that t equal to 0 or transient business has gone out of question, and we are not talking about steady state representations. So in steady state also, since it is varying, the sine omega t is a varying quantity, this do exist. Okay, So IT can be calculated as this C dV by dt, and this is the value of V we have, and accordingly if you take that, this is what you have as IT, and this is IT 1 by C omega, and this is cos omega t, and I can write this IT as this relation. So what happens in case of a capacitor? When a sinusoidal source is connected to a capacitor, current does flow. And what kind of current flow? That current flows, that amount of current, or the peak value of current is something like this, root 2 V upon 1 by C omega. So this is kind of a what you can say, kind of a resistance, which you can say is acting, as we did in the earlier analysis, it was by R. So instead of R, it is 1 by C omega here. So this is one thing which happens with T, and the other thing is there is a phase difference. So having a capacitor in a circuit gives the currents to be divided by certain value, and then it also shifts the waveform. So current is shifted by 90 degrees in a capacitor, and that shift is called a leading shift because it is plus here, so it is a leading shift. So if you see, this is the waveform of current which is shown here, IT, and this was the waveform which was source waveform. So this is how a voltage and current variations are there in case of a capacitor. And if you see, it is very difficult to write the way the things in a very, the way it is written is not very elegant, because the changes due to capacitor for current not only happens in the magnitude, okay, V by R business, but also in the phase. So phase also gets shifted. So capacitor has the effect of shifting the phase, but frequency remains same. So shifting of phase and value of peak is changed. Let's see what happens in case of a phasor representation. So same representation we are taking here. We are assuming a I phasor flowing, and we say now this is JXC. Let us see what this JXC is. So if I go with this representation, which we have done for this analysis, I am taking Q from this itself. So this is represented here by I, okay, I phasor, and this is the same V, okay, VT. And if you see this 1 by C omega, it has come over here, it is a value, so you can divide it, and this shift is basically shift in V sine omega t, okay, and that shift is basically coming over here. So now what we are doing is we are writing this phasor I happens to be V phasor upon 1 by C omega, and there is a shift in the phasor by 90 degrees leading, that is 90 degree lead shift is there in the phasor. So this C omega introduces this, or I can write this as this, because e raised to power j omega basically gives you j here, and I can write I as V upon JXC. This is very important representation in a way that it is exactly the same representation which we have for a simple steady state DC circuit, V by R, I is equal to V by R, except for the fact that here R is imaginary, but nevertheless the representation wise it is exactly like I is equal to V by R. So this is very elegant, not only representation wise but also calculation wise. So if you see, this representation is difficult to put in equations, but this is very easy to put in equation. We'll see in the later process that this is used for writing the equations for AC circuits. Anyway, so let us try to see the phasor diagram. So if this was V phasor, V star, then I star is this, I dash is this, I phasor is this, which is equal to V upon j omega c. So this is exactly representation of like V by R, except for the fact that V and I are now phasors and they can shift in they have shift in directions also. Okay, so there is a time shift between them, and the impedance appear, or the resistance kind of appears in a imaginary form. So this is what happens in a phasor representation of capacitor. Now let us see about phasor representation of inductor now. So here also, if you see the same style we are applying for what we did for capacitor. This is root 2 V sine omega t is the voltage, and then we are trying to calculate the value of IT using this relationship, and this is what we get. And here you get this as minus cos omega t, and if you want to write in a similar fashion, then IT is basically some V sine omega t, the input voltage, divided by L omega, similar to what we have for a resistance. But one more thing happens here, this shifts the waveform by minus 90 degree. So an inductor will come like a resistance plus a shifter in the waveform. So the IT will be out of phase by minus 90, or you can say 90 degrees lagging current would be there. In capacitor, you call the same current as leading current by 90 degree. So here we have the voltage put over here, V sine omega t, and this is pi by 2, and if it is a inductor, it will start from here. There is a lag of, the current has a lag of 90 degrees. So this is current and this is the voltage waveform. Now let us see the same fact in phasor domain or in phasor representation. So here the same V is represented as this, the same I comes about here, and now let us see the calculation of I using this part. So I am writing IT, this IT in phasor form. In phasor form, this is root 2 sine omega t phasor, that is V phasor, which is this itself, V angle 0. And then there is a shift of 90 degree, rather minus 90 degree, which is shown in this way. And there is L omega division, or this e raised to power j 90 is equivalent to minus of j. So now what we can say is, if you put in this form, it is again a very interesting form, that is I is equal to V by R form. So what we had for C, here also we have for omega L is the kind of resistance, which also has a kind of shift. So here the resistance is again imaginary, of course positive one, and it is V divided by that one, that is I upon V by R form. So you can say it is a kind of Ohm's law, very elegantly written in phasor representation. Here Ohm's law is not very elegant because it shows that it's affecting many things, but here it appears. So the equation wise, in fact, both are same. Only elegance is in the representation, and this elegant representation gives us computational advantage. So let us see the phasor diagram now. If this was V, then I should be, because it is shift of J in a negative, that is in this direction minus 90, and that is how you call the current is lagging. So I upon V upon kind of R, or you can say j omega L. Okay, so inductive reactance. Now if you have a want to look at a general phasor, about what kind of a phasor circuit involving phasors would like, I'm just giving you a visual impression that there will be a phasor voltage. This is obviously equal to V sine omega t. This is another voltage source, which is V2 RMS sine omega t, and with theta to shift phase as compared to 0. And this is current phasor having phase shift of theta 3, all of them having the same frequency. And these are the element. R1 remains R1. This JX1 obviously tells you what kind of element it is. It is inductor, because JX1, if you see, is an inductor. And similarly, JX3 is a capacitor. Minus JX2 is a capacitor. This is resistance. This is inductor. So it appears that we can represent this circuit. Of course, the elements are now complex, that is R, here it is real part and this is imaginary, and this is having an imaginary value I with them. Okay, so these are phasors. So resistance and phasors, so this is a general phasor circuit which we are going to have if we use the representation of sources in phasor form and R and X in phasor form. And this looks quite very straightforward for making the computation, as compared to if you go for sin omega t, then you will see how difficult it becomes writing the equation. Anyway, but here this is just to show you how a general phasor would look like. I'll stop here to okay, we'll just see this part, that is RLC series circuit. So here I am trying to show you various elements coming together and how this circuit looks in phasor form. So now here you have RLC all together, and we are trying to see how we are having the circuits. So VT, this is the time representation of voltage, V root 2 V sin omega t. Okay, and this is R, L and C. Okay, if you want to write the equations, try yourself. You will have to write first the integral and differential forms if you want to write I for this. Okay, LdI by dt and integral Ci, and add them to 0 and then assume the value of V and then assume the value of I, something like that. The writing of equations become quite tricky in this case. Just try to write it yourself. Let us see if you are able to do it. But what I am interested here to advance, or you can say advertise, is why not to do in phasor form. In phasor form, this representation becomes quite elegant. That is, let us see, this is V, so V minus IR, so V is the phasor voltage, I is the phasor current, so IR is the drop here in R, then j omega L times I is the drop over here, and plus 1 upon j omega C I bar is the drop in this. So it is like I am writing a simple Ohm's law equation having 3 resistances in series. Of course, these resistances are not all real but imaginary values. Except for that, it is exactly the same way which 3 resistance would have given me the equations. Okay, so only difference is all this becomes phasors. So this is of course imaginary value, IR phasors and VR phasors, but as far as writing the equation is concerned, it becomes quite elegant. And compare this, if you are interested in writing this, try to compare these 2 equations. Okay, you will find that what advantage this phasor representation gives you. So further carrying out this further, this is I am representing this omega L by XL, omega C by XC. Okay, J I am deliberately keeping out because they are very important. You cannot hide them in XC and XL. So this is the equation, and you can write it like this: I, R and J, XL. And if you see, unlike resistances, you can cancel out the impedances here, reactances. We call this as inductive reactance because it is because of inductance, and this is capacitive reactance. They are all reactances. Another names are also there. Somehow you will find susceptance and all the other things, but inductive reactance and capacitive reactance, and they cancel out here each by having subtracting them, and you can write V is equal to R plus JX, and XL is XL plus XC. And what you find this relation V is equal to IZ, where V is there, I is there, and Z is now a complex quantity. Okay, so this is a complex quantity. That is what Z is, and this complex quantity can be written as in a form of angle and magnitude. So Z is the magnitude, Z magnitude and theta, and this is R plus Jx, and the magnitude Z is this much, R square plus X square, and theta can be calculated as this way. So this is how this representation allows us to write the equation in a very simple form and analyze this analyze circuits having sinusoidal sources. Of course, the sources, if there are multiple sources, then they should have same frequency, then only you can calculate for same omega L and omega C. So that is always taken as given. That means it should be there, not a different. If there are different sources having different frequencies, then you cannot apply Phasor form, please remember, because you cannot calculate j omega L and j omega C. There are 2 omegas, maybe n omegas, and different values are possible. So we are assuming that all the voltages and current sources are going to have same frequency, which is quite good assumption as far as practical circuits are considered, especially in power engineering. Okay, all our household sources are 50 hertz. Okay, all the currents and voltages we are going to see are in 50 hertz. So this is what we are trying to see. V is equal to IZ. You can call it as Ohm's law in Phasor form. V is equal to IZ, or other way around, you can write I is equal to V into Y, where this is admittance, this is called impedance, this is admittance, and where admittance Y bar is equal to 1 by Z bar, and that is sometimes G plus JB, that is put in this form. When you write reciprocal of Z, then this G part is called conductance, real part, and JB is the susceptance, which is the imaginary part. So Y also comes in, that is admittance comes in complex form as you get for Z impedance. Now let us try to draw phasor diagram. Phasor diagrams are very intuitive insight into, gives us very intuitive insight into the circuit. It gives them some good ideas. So let us try to see phasor diagram for this. So this phasor diagram part 1 we'll take first, and then we'll go for part 2, that is exact phasor diagram. So when I'm going for part 1, I'm talking about only conceptual phasor diagram. If you have a phasor V like this, and if you have a current phasor I, so I have drawn like this, some angle theta, assuming that this JXL is more effective than JXC. Okay, so XL minus XC, if you see, is there. Okay, XL minus XC is there. So let us assume that effectively L is more, XL is more than XC, and therefore the current would be inductive, therefore it is lagging by V. Okay, it is lagging over here because it is R and XL. So if this is I, then the voltage drop in XL would be at 90 degrees here. Okay, 90 degrees this way going up, and if it is in a XC, it will be 90 degrees downwards. Okay, so current and voltage. So this is basically VL, voltage in I will be leading the current in case of lagging, in case of a inductor. Okay, and here it will be VC will be leading I. So this is how the relationship between voltages in reactances are there, and relationship between voltage and current in general. Now we'll see the exact phasor diagram here, which we have drawn. This is the reference I have taken, V as a reference I have taken. So this is my reference phasor. Now this is the current flowing I, and this is the drop I bar R. So in current they are in phase. Okay, in resistance the voltage and current are in phase. So this is IR, so resistance, voltage in the resistance, you can call it as VR if you want. They are in the same phase as I. Now at 90 degrees I am saying it is VXL, that is this part, VL, and this is at 90 degrees, and this is VC, and since it is on the same, you can say 90 degree the position, so you have to subtract it. So the reactive voltages VC and VL, if you subtract it, VC minus VL minus VC, where VL is larger we assume, then this is the resistance, this is the voltage here we have. So this is voltage in quadrature to I, and then when you add these three voltages IR, VL and VC, VL minus VC, that would come to equal to V bar this, then only it will be V minus B will be equal to 0. So that is a phasor diagram of a RLC circuit. So I will stop here for now, and just to keep the video short. Thank you.